Hello friends. Imagine you have a row of storage boxes lined up side by side. You fill them one by one, and then you run out of space. The boxes right next to yours are already taken. You cannot just grab 2 more and keep going. That is exactly the problem your computer runs into with a regular array. Arrays need contiguous memory, one solid unbroken block, reserved up front. If you need more room and that block is taken, you are stuck. You either move everything to a bigger block, or you over-allocate and waste memory you never use. Neither feels great. So the question becomes, what if your data did not have to live next to itself at all? In this video we are going to answer that with a structure called a linked list. Next up, let's look at exactly what that structure is made of. Alright, so here is the core idea. A linked list is made up of individual units called nodes. Each node holds 2 things: a data field which stores the actual value, and a pointer which stores the address of the next node in the sequence. Think of it like a treasure hunt. Each clue does not just give you information, it also tells you exactly where to go next. In our diagram, the first node holds the value 10, and its pointer leads to the node holding 25. That node points to the node holding 40, and that final node's pointer holds null, meaning the chain ends there. The node at the very beginning is called the head. It is your entry point into the entire list. Next, let's actually walk through this chain and see how traversal works, step by step. Alright, now that we know how nodes and pointers chain together, let's actually walk through a list. Here we have 4 nodes holding the values 12, 7, 31, and 45. The head pointer points to the first node, 12. That's our starting point. We read the value 12, then follow the pointer to the next node. We read 7, follow the pointer again, then 31, then 45. At 45, the pointer holds null, so we stop. That's the end of the list. Notice we never jumped directly to node 3. We had to walk the chain one step at a time. That's what traversal means, following pointers in sequence, from head to null. The trace table below tracks exactly what we visited and when. One step, one node, one value at a time. In the next slide, we'll see why this pointer-based structure gives linked lists a real edge over arrays when inserting or deleting data. Alright, now that we know how traversal works, let's talk about where linked lists really shine and where they fall short. Imagine inserting the value 30 between 20 and 40 in an array. Every element after that point has to shift 1 position to the right. That's order n work. In the worst case, in a linked list, you just rewire 2 pointers. Node 20's next points to the new node, and the new node's next points to 40. Done. That's constant time, assuming you already have a reference to node 20. Deletion works the same way. Skip a node, rewire the pointer around it. No shifting. But here's the trade-off. Arrays give you instant random access index straight to any element in constant time. Linked lists can't do that. You always traverse from the head. Next, let's pull all of this together into one clear mental model. Alright, let's bring it all together. A linked list is a chain of nodes, each one holding a value and a pointer to the next. There is no fixed block of memory. The list grows and shrinks dynamically, one node at a time. Here are the highlights to remember. Insertion and deletion at a known position cost constant time, because you are just rewiring pointers. Random access costs order n, because you have to walk the chain from the start. Arrays flip that trade-off exactly. Neither structure is better overall. They solve different problems, and knowing which to reach for is the skill. The linked list you have seen in this video is called a singly linked list. Each node points in one direction. Next up, we look at doubly linked lists, where each node points both forward and back. That small change opens up a lot of new possibilities. See you there, friends.